Time to start. So today we'll finish off chapter 11. We've got the hydration reaction and the hydroboration oxidation reaction of alkynes to talk about. We're kind of in the middle of the hydration. Then we're going to talk about acetylide ions and how they can be used to form carbon-carbon bonds. And then that will set us up for a discussion of how to plan a multi-step synthesis. So with the hydration of an alkyne, we told you that in analogy to the hydration of an alkene, the more substituted alcohol is formed. But when it is an alkyne that's being hydrated, we form an enol, and that enol tautomerizes to give us a ketone. So we drew the mechanism of the tautomerization at the end of class on Wednesday. So we're not going to go over that right now. But the formation of the enol intermediate is different from the way it is presented in the book. This is the second reaction, like the hydrohalogenation of alkynes, where the book has oversimplified things and they've shown a vinyl carbocation intermediate, which we told you earlier on is unstable and too high in energy to form. It's also suspicious that the mechanism in the book doesn't use the mercury, so it wouldn't make sense to use mercury in a reaction if it wasn't playing a role. So we have a mechanism that I'll show you now, which is more complicated than the one in the book, but it does make more sense because it uses the mercury and it avoids a vinyl carbocation intermediate. So if we look over here at our periodic table and we look at the position of mercury, we see that it's kind of on the right side of the transition metals. So transition metals are stable as cations, but because they are further down in the rows of the periodic table, they also have d electrons. So those two features of mercury, the fact that it is a fairly stable cation and that it has d electrons, make it useful in this hydration of alkynes and allows us to avoid that high energy vinyl carbocation. So because our mercury cation is electrophilic, it's Lewis acidic, it shouldn't be surprising that the pi electrons of the alkyne will attack the mercury. But if that's all that were happening in the first step, then we would end up with the vinyl carbocation. So as that takes place, before we form the vinyl carbocation, we can use one of the lone pairs of electrons on the mercury to come back down and form a three-membered cyclic intermediate that looks very similar to the halonium ions that we form when alkenes and alkynes react with bromine or chlorine. Okay, and so this is strained. It has a positive charge. It's very reactive, very electrophilic. So once we form this species, which we could call a mercurinium ion, then it is going to be attacked by water. And it's going to be attacked by water at the more substituted carbon. So we know that when we have halonium ions or protonated epoxides, our nucleophiles open those three-membered rings at the more substituted carbon because the bond breaking is more advanced than the bond forming at the transition state. So you have a partial positive charge, and that partial positive charge is more stable on the more substituted carbon. So that was the explanation we used to explain why epoxides are opened at the more substituted carbon when we use HX. It was the explanation we used why water opens a halonium ion at the more substituted carbon when we make a halohydrin. So this is the same explanation applied to now our third reaction. So water opens this mercurinium ion at the more substituted carbon. There will be a partial positive charge on that carbon in the transition state. And then we have to deprotonate the oxygen using another equivalent of water, and that gives us this intermediate right here. And what can we call that intermediate? When we have an alkene with an alcohol attached, what do we call that? We call that an enol. And what happens to enols? Okay, they will undergo tautomerization to afford ketones. So this enol has a mercury ion attached to it, but it's still an enol. So it will react with H3O plus, protonating the alkene to generate the resonance stabilized cation. Water will deprotonate the OH to give us the ketone. Again, that's an equilibrium, but that equilibrium is very strongly favored in the direction of the ketone. Okay? So once we get to this ketone, we know our final product is a ketone, but this is not our final product because we still have the mercury ion attached. The mercury ion has done its job. It was used to make sure the water attacked at the more substituted carbon and to avoid a vinyl carbocation intermediate. But now we need to get rid of the mercury. And so the way we do that is we use our aqueous acid. And remember, anytime we have sulfuric acid and water, we can just write H3O plus because we will have plenty of that available in our solution. So we'll learn much more about carbonyl groups in Chem 352M. We'll spend about a third of the time in the class, second semester, with the chemistry of carbonyl compounds. And you'll get used to seeing this type of step quite frequently, protonation of the oxygen of a carbonyl group. We have two lone pairs here. This is basic enough that strong acids will protonate that oxygen. But in this case, as we protonate that oxygen, we would be generating a cationic intermediate, but we already have a cation in our molecule, and that cation is simply eliminated. So our mercury cation comes off and is regenerated, and then we form another enol by this particular step. And so that enol will undergo a second tautomerization to give the final ketone product. Okay? So this mechanism we've drawn for you here is lengthier than the one in the book, but it makes more sense. It uses the mercury cation. It uses the mercury cation in a way similar to what we've seen in other reactions. If you look at the first three steps of this mechanism, they're exactly the same as what happens in a halohydrin reaction. If you just replace the mercury with chlorine or bromine, you'd have the same three things happening. You'd form a three-membered intermediate with a positive charge. You'd have water attack the more substituted carbon, and then you would deprotonate that water. So we've seen these first three steps before. The next two steps, which I didn't draw out for you on the board, are the tautomerization steps that we showed you at the end of class on Wednesday. The last two steps of the mechanism are the same as those, a second tautomerization. And so there's really just one step here that's a little bit unusual compared to the ones we've seen before, where we protonate this oxygen and the mercury is eliminated out, giving us the enol. Okay, so it's a fairly lengthy mechanism, but if you divide it up into the four segments, it's more manageable and understandable. And importantly, it helps us understand the role of the mercury and why we end up generating the more substituted enol, which then gives us a ketone. Questions? Yes, Parker. Are you talking about going from the enol to the ketone? Uh-huh. Yes, by H3O plus again. Yes. Right. So there's a lot of proton transfers here. So the two steps we didn't draw, protonation of the alkene, followed by deprotonation of the oxygen. And then we reprotonate the oxygen in conjunction with losing the mercury. So it seems like a lot of proton transfers, and it is, but that's how the mechanism proceeds. Other questions? Yes, please. So that's not in the book, right? Because the book does the shortcut version and just makes a vinyl carbocation. So what you would do is just look at the tautomerization steps. Those are the only ones we didn't draw for you here on the board. And those are the ones that we drew on Wednesday. So you would just substitute those in for these arrows that we didn't show you. Okay? Have a question in the back there? Yes. Okay, that's a good question. So it is the same explanation that we used for protonated epoxides and for the halonium ions. Whenever we have a three-membered intermediate and we have a positive charge on one of the atoms in that three-membered ring, when we open the ring, the bond breaking at the transition state will be more advanced than the bond forming process. So we end up with a partial positive charge on the carbon that is being attacked. And that partial positive charge is more stable on the more substituted carbon versus the less substituted carbon. So we have a lower energy transition state and therefore a faster reaction for attacking this carbon versus attacking that carbon. So it's the same explanation that we used for epoxides being opened with HX and for the halohydrin reaction with bromine or chlorine and water. Okay. Other questions? So this reaction, if we use propine, we will obtain a ketone, acetone in this case, because the water attacks the more substituted carbon. What if we wanted instead the less substituted enol, which would tautomerize to give an aldehyde? That's what we have when we have the carbonyl at the end of the chain, as opposed to a ketone, which has it inside the chain. How could we make an enol that would give us an aldehyde instead of a ketone? What reaction could we use? It's not a trick question. Yes, in the back there. Exactly. So in the same way that hydroboration oxidation gives us the less substituted alcohol from an alkene, it will give us the less substituted enol when it reacts with an alkyne. Okay? You see that up here with butane. We could draw it on the board with our propine that we've been using as an example. So if we react propine with BH3, remember there's different ways to draw it. If we the THF complex of BH3 is one that we can use. So the boron is going to end up on the less substituted carbon. So our borane would look like this. I'm going to go ahead and draw the hydrogens in to remind us that the addition of BH3 across an alkene or an alkyne is a syn addition process. So these two groups are going to be cis to each other. And then we would use hydrogen peroxide and hydroxide. That's going to convert our organoborane into an enol with retention of the configuration. And then once we get that enol, it's going to tautomerize to give us an aldehyde. Okay? So with terminal alkynes, we would obtain a ketone with water, sulfuric acid, and mercury sulfate. We would obtain an aldehyde if we used hydroboration followed by oxidation. Okay? What if we used an internal alkyne? So let's say we had an alkyne of this type. Would we get the same products or different products from a hydration versus a hydroboration oxidation? Yes. Okay. So I've drawn it with the R. That's a good observation. If the R groups are the same, would we get the same product or different products? Okay, good. So if we have an internal alkyne that is symmetrical, and these R groups are the same, then these two reactions, the hydration and the hydroboration oxidation, would give the same ketone. Okay. If we had an unsymmetrical alkyne like this, where those R groups were different, you would get the same result in both cases, but it would be a poor result in that you would get a mixtures of products. Why? Why would you get mixtures of products from a hydration and a hydroboration oxidation of this type of alkyne? So, yes, go ahead. Yeah, exactly. So we don't really have a vocabulary word to describe it. Racemized, it doesn't exactly fit, but we know what you're saying. So that's a good explanation. So unlike alkenes, where if you can have an alkene in the middle of a chain, and you can have a more substituted carbon and a less substituted carbon. But when we have an alkyne, because of the triple bond and the sp carbons, you only have one group other than the other alkyne carbon bonded to it, right? So these groups, they might be slightly different in size. There might be a bigger group and a smaller group, but there's only one group attached to each of the carbons of our alkyne. And so what that means is that there's not going to be much of a difference in those carbons when we do a hydroboration. We'll get the boron on each carbon. We'll get both enols. And the same thing would happen if we were doing a hydration. The water would attack both carbons and we would get both products. So if we used an alkyne such as this, you would get a mixture. I'm running out of room here on the board, but you would get a mixture of ketones looking like this, right? These ketones are constitutional isomers of each other, and you'd get probably pretty close to a one-to-one mixture of those ketones. And so what that tells us is that these addition reactions of alkynes work the best either with terminal alkynes or symmetrical internal alkynes. Those are the ones that will give you a single product. Except for the halogenation. If you look at the halogenation, that's the one where we're adding the same groups to both carbons. So we're going to get a single product regardless of what type of alkyne we use. Okay? Any questions about that point? So these reactions are best with terminal alkynes and symmetrical internal alkynes. All right. So let's talk about acetylide ions. We've mentioned them previously. We know that they are strong nucleophiles. We know that they are formed by the deprotonation of a terminal alkyne, sorry. And we have to use either sodium amide, NaNH2, or sodium hydride, NaH, as our base. And then if we add a primary alkyl halide, that acetylide ion can react with that primary alkyl halide in an SN2 reaction, giving a new alkyne. Okay, so we had 3 carbons in our alkyne, 2 carbons in our alkyl halide. So now we formed a new alkyne that has 5 carbons. And that shows us why these reactions are useful. They allow us to make longer chain molecules from smaller precursors. Okay? And that's very, very useful. Most of the reactions we've learned in class until now have been forming carbon heteroatom bonds, carbon hydrogen bonds, carbon-carbon pi bonds between carbons that were already bonded to each other. But this is the first reaction where we can take 2 carbons from separate molecules, they aren't bonded to each other, and join them together to make a longer chain molecule. Technically, in chapter 7, when we learned about cyanide as a nucleophile, that was a way of making a carbon-carbon bond. But cyanide only has 1 carbon, so you can only extend your chain by 1 carbon with cyanide. So these acetylide ion alkylations are much more useful because you can extend your chain by more than just 1 carbon. Okay, and we could use, if we used acetylene, then we could do 2 consecutive acetylide ion alkylations. We could deprotonate with sodium amide. We can add a primary or a methyl halide, right? Iodomethane would work. So in this case, we could form our propyne, and then we could react that again with sodium amide or sodium hydride. And in this case, we would end up with a 6-carbon alkyne. Okay, so with acetylene, you have the ability to add 2 consecutive halides, but they must be either methyl halides or primary alkyl halides. The acetylide ion is a significantly stronger base than any of the other nucleophiles that we saw in chapter 7. And so due to that fact, it is more prone to promoting elimination reactions. So it will only undergo substitution with a primary alkyl halide. If you were to react an acetylide ion with a secondary alkyl halide, such as this one, instead of substitution, we would just see an E2 reaction. It would give us an alkene, and we just get our acetylene back. Okay. So, whereas our strong base, strong nucleophiles from chapter 7 will do this with tertiary alkyl halides, an acetylide will perform an elimination with both tertiary and secondary alkyl halides. So it has to be a primary alkyl halide if we want the substitution reaction. Questions? So because of the ability to form longer chain molecules from shorter precursors, the alkylations of acetylides are quite useful and have been used for many purposes. The book shows you a couple of these reactions here on the screen. So in the first one, I'm not sure, to be honest, why they added water here. It's not really necessary because your acetylide will displace the iodide. You would end up with a salt between the iodide and whatever your cation was, probably a sodium cation. So maybe they're using water to dissolve the byproduct, but you don't need it to get the organic product here, okay? So we're forming this carbon-carbon bond, and then this compound was used in a multi-step synthesis to afford capnellene. This next example here, the book has left out some key details that are actually very interesting about this reaction. So they don't tell you that you would need 2 equivalents of the base in order to get the product shown here. What would happen if you treated the molecule shown here with 1 equivalent of base? Parker? Okay, so 1 equivalent of base would deprotonate the most acidic hydrogen in that molecule, and the OH is more acidic than the terminal alkyne, okay? And so if we deprotonated this oxygen, and then we reacted that molecule with this primary bromide, what would happen? That is a reaction from chapter 9, so hopefully you know what it is. Noah? Yeah, you do a Williamson ether synthesis, and you'd make an ether product, okay? If we use 2 equivalents of base, then our second equivalent is going to deprotonate the second most acidic hydrogen, which is going to be the one on the alkyne. And so then we would have a dianion. Now, why would that dianion react at the alkyne to give the internal alkene as opposed to reacting on the oxygen to give the ether? Yes? Very good. Because the alkyne is less acidic, its conjugate base is more basic, okay? And we learned back in chapter 7 that in most cases there is a correlation between basicity and nucleophilicity. There were a couple of exceptions, but in most cases, if you're comparing bases, you would say that the stronger base is the stronger nucleophile. So if we have a dianion, we can conclude that the more basic of those 2 anions is the one that's going to be more nucleophilic. So indeed, if you react the dianion with 1 equivalent of this alkyl halide, you would then form the carbon-carbon bond. And then here, there is a reason to add the water. We would use the water to protonate that oxygen of the alkoxide to give the final product. Okay? Question, Parker? Here? I mean, you could, so the problem, for example, if you, with most alkyl halides, so you're saying why would you do it in 2 steps as opposed to just all together? Yeah. So you'd have a reaction between your halide and your base, and then up here you just see an elimination. You know, these bases are really good for elimination, so you just eliminate your alkyl halide. So that's why you would want to do it in 2 steps. Step 1, make your acetylide. Step 2, do your substitution. That will prevent the base from reacting directly with your alkyl halide. Okay, that's a good question. All right, so a lot of subtle details here that were kind of skimmed over, but important things to remember. When we treat a molecule with 1 equivalent of base, we're always going to deprotonate the most acidic hydrogen. That might not be the one we want, and so if we wanted to deprotonate the second most acidic hydrogen, we would need 2 equivalents of our base. And then if we have a dianion, the more basic of those 2 anions is the one that would be the more nucleophilic. So those are a couple principles we can learn from this interesting reaction. Other questions? Okay, so our acetylides will react with primary alkyl halides by substitution. Of course, secondary and tertiary will undergo elimination, but they will also undergo carbon-carbon bond formation with epoxides. We know that strong nucleophiles will open epoxides, and because our acetylide ion is a strong nucleophile, it will perform an epoxide ring opening. And based on what you learned previously about ring openings of epoxides with strong nucleophiles, you should be able to look at this problem and determine the major product or products. So go ahead and get your eye clickers out. You can talk to your neighbors and determine the major product or products of the reaction shown here. All right, let's try to get our final answers in the next 10 seconds or so. Okay. All right. Any more? Going once, going twice. All right, that looks like everybody. So which carbon of an epoxide does a strong nucleophile attack? More substituted or less substituted? Less substituted. So what's our product? A, exactly. And this is one of those cases where there's not enough reasonable answers, so we just threw up kind of a nonsense choice here. Hopefully nobody went for that. That's kind of a fault of multiple choice formats sometimes. Yes? I mean, you can get compounds that have 3 alkyl groups on an oxygen and that oxygen has a positive charge. I've never seen one quite like that, though, so I don't think that you could make that. Yes?
I was a little confused because I thought that the epoxide would be slightly open on that left side.
Okay.
It goes towards the less substituted one.
Okay. So when you have the bond breaking more advanced than bond making, that's only if you protonated the epoxide first. So that only happens with HX. And that's one of those things, there's a question about that earlier in the class in regards to this hydration mechanism. That's one of those concepts that's tough to solidify. We've learned so many reactions in this section of the class, and there's a subtle difference between opening an epoxide that's protonated versus opening an epoxide that's not protonated. So the goal is, if you missed it now, hopefully you won't miss it when you go take the exam. But anyway, it's because we don't protonate the oxygen. It's just a straight SN2 reaction. And so the less substituted carbon is the one that gets attacked. Question, Parker? So that wouldn't work in this case, because if you protonated the oxygen, added the acetylide, it would just do an acid-base reaction.
Yes, and in this case, but I mean, in a more general case, can you protonate that oxygen aldehyde with only with HX?
No, H2SO4 will also work. So you would use water or an alcohol as the nucleophile if you were protonating with H2SO4. So that would give you either a diol or an ether product. Okay. All right, and so then we add the water in the second step to, and then this particular reaction didn't show any stereochemistry. This is a stereocenter here. Would the stereochemistry at this carbon be changed? Would it be inverted or would it stay the same? It would stay the same, right? Because we're attacking this carbon, so that carbon is unchanged in this particular reaction, okay? But let's say we had, if the less substituted carbon was a stereocenter and it was attacked by an acetylide, what would happen to its stereochemistry? It would invert, exactly. So if your acetylide is attacking an epoxide where the less substituted carbon is a stereocenter, it will invert, okay? All epoxide ring openings proceed by inversion at the carbon that is being attacked, regardless of whether it's the more substituted or the less substituted, okay? So a lot of details there on epoxide ring openings. All right, so let's talk now about the process of designing a multi-step synthesis. If we're asked to make a compound, a complex molecule from simple starting materials, but we can't do it in one step. We have to design a multi-step process to get from the starting materials to the products. There's a variety of ways to solve such problems, but in most cases, the easiest way to do it is something known as retrosynthetic analysis. That's the process of working backwards from the desired product to readily available starting materials. Okay, some cases you might have one starting material, other cases you might have more than one if you needed to do a carbon-carbon bond forming reaction to make your product. So I've told you previously that arrows are part of the language of organic chemistry, and when we are working backwards, when we're planning for a multi-step synthesis and doing a retrosynthesis, we have a special type of arrow that we use, okay? So if we drew our target compound, and then we made an arrow like this, that sort of an arrow specifically means that we're working backwards. And so we would then draw the immediate precursor to this target compound. As we're doing a retrosynthesis, we ask ourselves, what compound could we make this target compound from in a single step? Okay, so we would have that precursor there. And if that was not this readily available starting material we could use, we would keep going backwards. We would generate another precursor. And then eventually, we would make it to the starting material or starting materials that we could use. If you were doing this process in a lab, the starting materials you'd be allowed to use would be ones that you could buy for a reasonable price from a chemical supplier, or they would be compounds that have been synthesized previously, and there are published procedures for making those compounds. That's what we would consider a readily available starting material, something that you could either buy or synthesize using a known procedure, okay? But in class, usually we give you constraints. We'll either give you structures as starting materials, or since alcohols are common starting materials, we would say you can start with alcohols that have 3 carbons or less or something like that. And we would consider that readily available starting materials. So you might wonder, why do we work backwards instead of working forwards? Well, the truth is you can do it either way. You can solve the problem however you want to. But for most people, working backwards is better. The reason is that from our readily available starting materials, we have a whole bunch of reactions that we can do. But maybe only one of those reactions is going to be the one that would get us to the target compound. If we use alcohols as our starting materials, In chapter 9, we learned a whole bunch of different reactions of alcohols. And so if you worked forward, you'd have a greater chance of getting on the wrong path that wouldn't take you to your final product. If you ever worked those maze puzzles as a kid, where you had a starting point and then you had to draw a line that got you to the end, you probably found there were a lot of dead ends if you work forward. You may or may not have recognized kind of a shortcut. If you start at the end, there's oftentimes less dead ends, and it's easier to find the path that gets you through the maze. That's the way synthesis problems work, is you're less likely to run into a dead end if you're working backwards. Also, for most people's brains, it tends to be easier to take your complex product and simplify it step by step to get to your starting material rather than doing it in the other direction. So for those reasons, I recommend that you use retrosynthetic analysis to solve a synthesis problem. Question? Yes, you do have to write it forward, and we'll stipulate. You'll see the instructions. It'll say you should use retrosynthesis, but we're only going to grade the forward direction. So to get the credit, you have to then, as a final step, write it out in the forward direction. Yes, question? Okay, that's a good question. So when you are writing out a synthesis problem, you don't have to draw curved arrow mechanisms. You just have to draw the reagents and the products of each step. We only want you to draw the curved arrow mechanisms on the questions where we explicitly say, draw the mechanism. Otherwise, you'd spend all day on your synthesis problem. So we don't want that. So the process that you, again, there's different ways to solve these problems, but we'll go through a process that works in most cases. So the first thing you want to do is compare the carbon skeletons of your target compound and your starting material or starting materials that you're allowed to use. And the first thing you want to see is, do they have the same number of carbons? If your target compound has more carbons than the starting materials you can use, you know that you're going to have to perform a carbon-carbon bond forming reaction to make that target compound. And what carbon-carbon bond forming reaction have we learned? Acetylide ion alkylation. So you'll know right away at this stage of the class that you would have to do an acetylide ion alkylation with either a primary alkyl halide or an epoxide at some point in your multi-step synthesis. Okay? If the number of carbons match, then you won't have to do that sort of a reaction. But if they don't, you know at this point in the class that's the only carbon-carbon bond forming reaction we've learned. Okay? So that gives you a real big clue of what you need to have in your synthesis. The second thing you want to look for is you want to try to match up the locations of carbons in your starting material with carbons in your target compound. If you can figure out where those carbons are going to end up, that can help you figure out what kinds of reactions you would need to do. So once you've looked at the skeleton, you next want to look at the functional groups in your target compound, okay? And ask yourself, what reactions have I learned to install these functional groups? If you have a ketone, you're going to want to do a hydration of an alkyne. If you have a vicinal dihalide, you're going to want to do a halogenation of an alkene. So you look at the functional groups and you ask yourself, what reactions have I learned for installing these functional groups? And so these 2 points will give you some hints and ideas of the reactions that you'll need to use in the synthesis. So once you've done that, once you have an idea of what types of reactions, then you start working backwards from the target to the starting materials, okay? And as you do that, you want to make each successive precursor simpler than the target compound, okay? If you're working backwards and making the precursors more complicated, than what you started with, that's going in the wrong direction. So you always want to make it simpler. And at each step, you want to ask yourself, what molecule could I make this precursor or this target from in a single step? And you keep going with an eye on the structure of the starting material so that you're moving in the direction of those starting materials. Okay? And then once you've done that, once you've worked backwards, then you need to, once you've succeeded in reaching your starting material, then you need to write the synthesis in the forward direction. And when you write the synthesis in the forward direction, you don't need to draw the mechanisms. We don't want you to draw the mechanisms. That would take too much time and space. But we do want you to draw the reagents. You have to draw the reagents for each step. You have to draw the product of each step as you write the synthesis in the forward direction from starting materials to products. Okay? So let's do an example. Let's say that we want to make this ketone here, and we're going to make this ketone from compounds with 2 carbons or less. Okay? So how many carbons in our target molecule? 4. So we know we're going to have to do at least one carbon-carbon bond forming reaction, which tells us we're going to have to do an acetylide ion alkylation. So a good place to start is to look at our ketone and simplify it back to an alkyne. Okay? Now I made it easy for you. Do we have a reaction that makes a ketone in one step from an alkyne? Okay, which one? Okay, the hydration reaction. So let's go ahead. We'll draw our arrow from the ketone that we drew right here. So we can make this ketone directly from an alkyne. How many alkynes could we make this ketone from? Is there just one that would work, or are there 2 that would work? Yeah, I think there's 2 that would work. We could use 1 butyne, or we could use 2 butyne. In this particular case, 1 butyne is going to be better. And by the time we get to the end, we should see why. So I'm going to go ahead and draw 1 butyne as our precursor. Okay? All right, so we've succeeded in making it back to an alkyne. We were able to do that in one step. And since we know that we have to get back to compounds with 2 carbons or less, then we ask ourselves, how could we disconnect this alkyne to make 2 carbon building blocks? Okay. Yes, go ahead. Yep, so if we did an alkylation of an acetylide, we would form this carbon-carbon bond right here, and we would make that from the conjugate base of acetylene itself and an alkyl halide. We could use bromoethane, iodoethane, chloroethane. It wouldn't really matter. Okay. And then our acetylene, or our acetylide ion, that would be obtained from acetylene itself, right? Okay. So we've made it back to compounds with 2 carbons or less. Right? This was a short example designed to be finished in class. What if we would have tried to use 2 butyne? We could have gotten the product, but it would have been less efficient than this way. Why? If we used this instead of that. Yes? So this is symmetrical, so we would still get the same ketone in this case, but there's another problem. Right. Because of this stipulation that we had to use compounds with 2 carbons or less, we would have to disconnect each of these methyl groups separately, and we'd have more steps in our synthesis. So it's actually more efficient to use this alkyne than this alkyne. Okay? So now let's do the synthesis in the forward direction. Let's start with our acetylene. What are we going to react it with to deprotonate it? NaNH2. You could use NaH as well, but we'll use NaNH2. And then what are we going to react the acetylide with? Our bromoethane. Some synthesis problems make you go back to alcohols and not just any compound with 2 carbons or less. Could we make this from an alcohol in one step? Yeah, absolutely. We could use PBr3 or HBr to do that. Okay. All right, so we made our butine, and then how are we going to convert the butine into our ketone? What reagents are we going to use? Okay, so we'll use our mercury sulfate, sulfuric acid, water. That will give us the ketone. Okay, so straightforward, just a 2-step problem. One on the exam will probably have more than 2 steps. But now you know the pattern that you would use. So I would suggest practicing synthesis problems. That's the best way to learn them. There's a whole bunch of them in chapter 11. There's a section at the end of chapter 11 called synthesis. And we've assigned about half the problems because that's typically what we do to give you a manageable load. But if you need extra practice, you can work the other ones. Preston has put some synthesis problems on his TA page on Learning Suite. So go ahead and practice the process until you feel comfortable with it. And once you do, then you should be ready to take the exam. And good luck. Don't be afraid to take it today if you're ready, and enjoy the rest of your weekend. And we'll see you on Monday.